Welcome back, sharp minds. Today we are tackling question 23, which marks the absolute grand finale of our functions chapter before we launch our daily marathon straight into inverse trigonometry. Take a look at these two conceptual mapping statements on your screen. Most students see an absolute value expression mixed with heavy quadratic quotient and assume they have to jump straight into messy, page long algebraic proofs or brutal quotient rule derivatives. Do not do that. This is an absolute time trap designed to drain your exam clock. So, before we look at the math, we are going to establish the two golden laws of calculus that allow us to classify both statements mentally in under 10 seconds. Now, a quick heads up. If you already understand these two graphical concepts completely, you can skip ahead directly to the timestamp on your screen to see the direct mathematical solution. But if you want to understand the why behind the magic, let's break down the rules of the game. So let's think sharp.
Hey thinkers, welcome back to Think Sharp Alley, where every turn leads to a smart solution.
Statement 1 concept, the 1-1 law. In statement 1, we have to check whether the given function is 1-1 or not. Remember, a function is 1-1 if it's continuous everywhere and if it's strictly monotonous. Strictly monotonic function means the curve moves exclusively in one direction. It climbs continuously or descends continuously without ever stalling or turning back. Because it never turns back to cross its own path, it passes the horizontal line test flawlessly. Any horizontal line you draw will slice that curve exactly once, which is the absolute definition of 1-1 function. If a continuous function is strictly monotonic across its domain, it is guaranteed to be 1-1. So let's check our function fx over here. Now if we look at the denominator, we have 1 plus modulus x. Modulus x is positive. So sum of two positive numbers can never be equal to 0, right? So this function is positive and defined at each and every point of the domain. So now let's check the monotonicity of this function. Let's say the first case x is greater than equal to 0, which means modulus x will be equal to x. So my function becomes x by 1 plus x. Now let's find its derivative to check its monotonicity, that is whether it is strictly increasing or decreasing. Here we will use quotient rule for the derivative. So f dash x is equal to 1 plus x whole square in the denominator and 1 plus x remains as it is. We differentiate x, so we get 1 minus x remains as it is. We differentiate 1 plus x and we get 1. Simplifying which we get 1 by 1 plus x whole square. Now remember 1 plus x whole square is always greater than 0 for all valid x in the domain. So the derivative f dash x is definitely greater than 0 for all x, which means the function is strictly increasing on this interval. Now the second case where x is less than 0. So which means modulus x is equal to minus x and the function becomes x by 1 minus x. Now let us find its derivative. Again using the same quotient rule we get this, which simplifies to 1 by 1 minus x whole square. Now clearly the denominator is always positive and hence f dash x is always positive for all x less than 0. So this means the function is also strictly increasing on this interval. So we get the function is strictly increasing across its entire domain without ever changing direction. So it will pass the horizontal line test flawlessly. That is, any horizontal line will cross the graph at most once. So which means this statement is definitely true. Now let's take a look at statement 2. Here we have to check whether this function is many one. Remember the golden rule. If a function satisfies these two conditions, first, it is continuous everywhere, meaning the curve never breaks, jumps, or blows up to a vertical asymptote in the middle. And second, it approaches the exact same finite limit, say L, at both positive infinity and negative infinity. Then that function is guaranteed to be many one. Now, if you really want to know why the second condition is mandatory, please watch this explanation. Otherwise, you may skip and go directly to the solution. Think about what this looks like on a graph. Let's say the limit extends to positive infinity fx is equal to limit extends to negative infinity fx is equal to L, which means this is the line. So the value of y is equal to L. This is the line L. And this also means that the function approaches L as x tends to infinity or negative infinity, which means the curve is forced to start at a height of L on the far left. So it goes something like this and is forced to return to that exact same height. So if it is going up, it will return to exact same height L on the far right. Now, if it leaves that height in the middle to go up like I have done, this creates a mountain, or it may go down. So that will create a valley. But either way, it structurally must turn around to head back to its destination at the other end. So the exact moment a continuous curve makes a U-turn, it automatically fails the horizontal line test, because any horizontal line that is drawn through that mountain or through that valley will slice the curve at least twice, proving that multiple different x inputs will yield the same y output. See, these two are different x. Let's call it x1 and it will give the same y output. x2, same y output. So this clearly means the function is many one. Obviously, there is only one exception. The only way a function could meet the same height at both ends and not turn around. So this turning is not happening. If it stays perfectly flat, that is fx must be equal to L, which means a constant function. So which means for different values of x, y will be same, L. So constant function is still many one, because every single x maps to that one value. That is why if the limits at infinity of a continuous function match, instantly it's a many one function, no derivative required. So let's check its continuity first. We can say fx is continuous. Why? For a rational function to be continuous on all real numbers, it means you must be able to draw its graph from left to right without ever lifting your pen. So there is only one thing that can rip a hole in a rational graph or blow it up to infinity. That is division by 0. That means if the denominator becomes 0 at some value, then the function value becomes something by 0, which is undefined, and that creates a vertical break in the graph, which will destroy its continuity. If the denominator never becomes 0, then no matter what real number you plug into x, you will always get a perfectly valid real number output. There are no breaks. Now, because our denominator is x squared minus 8x plus 18, let's find its discriminant, which is coming to be minus 8, negative. That means it can never equal 0 for any real number. This alone guarantees that our function is an unbroken smooth line across the entire x-axis. So it is 100% continuous. Now let us check the limit. Limit extends to positive infinity fx. So let's put fx. And we take x square common from both numerator and denominator, and the x square on the top and the x square on the bottom cancel each other out completely. And as x becomes infinitely large, any fraction with a fixed number on top and x on the bottom, like 4 by x, 30 by x square, or 8 by x, 18 by x square, shrinks down to absolute 0. And substituting those zeros in leaves us with 1 plus 0 minus 0, which is 1 in the numerator, and 1 minus 0 plus 0, that is again 1 in the denominator. So we get 1 by 1, which is equal to 1. And even if we put negative infinity in the limit, it does not change. So the limiting value is same for positive infinity as well as negative infinity, which means our function is definitely many one, and that means the statement 2 is absolutely correct. So the correct choice for this question will be option 1. Both statement 1 and statement 2 are true. Always use asymptotic limits to classify complex rational functions quickly without wasting time on massive quotient rule derivatives. Remember, building elite reflexes isn't about pulling cram sessions, it's about daily deliberate focus. On this channel, we analyze exactly one high level JEE question every single day to ensure your mathematical fundamentals remains sharp, fast, and completely unshakable under exam clocks. Think of this playlist as your essential daily revision ritual, just a few targeted minutes a day to lock in your execution speed and conceptual depth. Make sure to smash that subscribe button, turn on your notifications so you never miss a daily drop, and I'll see you tomorrow with our question 24. Keep pushing, stay consistent, and always think sharp.